everyone. This is Ishwarya Goyal.
And I'm Nilesh Agarwal.
From Towards Scaling Inference. Towards Scaling Inference is a place where you can learn about ML deployments from zero to scale. We are very excited to have Dan from Abnormal Security with us today.
Hello.
Hi, Dan. As the head of machine learning, he's leading a team of 40 plus detection and ML engineers, where they have built data processing and machine learning layers that detect cyber attacks by using variety of techniques, including aggregation systems, traditional machine learning approaches, and LLMs. Previously, he has also worked with Twitter. Thank you, Dan, for joining us today. So we would like to start the interview, Dan, by asking, what kind of business problems are you solving through AI?
So at Abnormal, our core goal is to stop cyber attacks and to identify the difference between regular traffic in customers' environments and malicious traffic. And so there's a lot of different kinds of cyber attacks that we focus on, but we mainly focus on the ingression point of incoming messages, either from email or other services, and the identification of compromised accounts and taken over accounts. And so the core AI problem there is a classification problem. Given some event, whether it's a message or an action that a user has taken, identify whether or not the sender of this message or the current operator of the account is an attacker that's trying to do something malicious. And so this is a pretty traditional problem to reduce to machine learning because of how sort of yes-no classification it is and relatively black and white it is. And so as a result, a lot of the core issue here comes to be around scaling the raw efficacy and the raw efficiency of the product that's solving this problem, as compared to something like recommender systems, where the actual framing of the problem can be equally difficult to the operation and acceleration of the problem.
Got it. And how do you currently deploy these models in production? Like, do you work with managed services like Hugging Face or AWS, or have you built your own infrastructure from scratch? I would also love to understand, like, what are the pros and cons of the approach that you have taken?
So we have a variety of different kinds of models that have different kinds of inference requirements and different kinds of operation requirements. We utilize what I sometimes like to refer to as a federated model architecture, where we don't utilize a single model, but we instead have probably hundreds of models that behave differently and either target different types of traffic or are very, very specific. Some are as simple as extremely simple decision trees that we build using an internal DSL for expressing these, and many are really large models that are like BERT or deep and cross networks that are deployed with TensorFlow or PyTorch. And so for our larger models that are a little bit more traditional, a little bit more similar to what you might expect in a centralized serving architecture, we deploy everything internally. We don't use managed services. One of the reasons for this is that we're dealing with extremely sensitive data, like with customers' internal emails, for instance, and going through managed services requires a very serious degree of security and compliance burden that's it's difficult to justify from our perspective. That there are simplicity benefits, absolutely, to working with managed services. There's benefits of being able to take advantage of latest advances in inference efficiency and efficacy improvements. There's advantages in being able to take advantage of like the massive improvements in efficiency that you get from batching. But with a lot of the things that we do, there's a trade-off between these kinds, the ability to have this kind of cutting edge adoption of newer technology and be able to remain safe and secure for the customers who are trusting us with their most sensitive data. And so this is a constant challenge across all different parts of our ML stack, and inference is just one place.
Correct. No, this is super helpful. And since you already told us that you're using TensorFlow and PyTorch to train these models, but while deploying, do you also use like some kind of quantization where you convert it to ONNX, TensorRT, or use some like optimization for a standard deployment? Are you doing anything in that direction?
Yes, we do use ONNX. It depends on the deployment. For our Torch models, we're utilizing ONNX, and we're migrating many of the TensorFlow models to ONNX as well. Where we use native deployments for a lot of the like internal DSL based models that we utilize. We have some scikit-learn models as well that we're deployed in native format. By and large, this isn't a like ideally we would like to standardize on a single deployment format. I think the complexity of our current deployments, it's more of a tech debt than like a explicit decision, but it would have a lot of different areas of consolidation in between feature serving and model training and model deployment and model inference. And so the consolidation on ONNX, while we've been very happy with ONNX and have gotten good results out of it, it hasn't yet been the top priority for team migration.
Got it. So you basically try to convert to ONNX, but is there any like technical or business reason why like you do or don't convert to ONNX? Like,
I mean, I think the biggest one is the internal DSL through which we run certain models is not out of the box compatible with ONNX. To be honest, I haven't done a deep enough dive into all of the different kinds of feature transformations that we have. Some of our models have some pretty looped together ways that they interface between the inference and the pre-processing of the data, and some of the abstractions that we've built for how the different stages of pre-processing, what gets encoded into the model binary itself and what gets referenced in code is a little bit different than what's standard from like some of the out of the box systems. And I'm not totally sure how well the conversion to ONNX will work with that interface. So I think that that's one unknown source of technical complexity that's been something that's stopped us from being confident that we would be able to complete a migration of all of our different types of models to ONNX. For something like a BERT model that's just running on the tokens of an email with the standard like word piece tokenizer, there's not too much complexity in the migration. And so that's like when we end also the benefit of getting it to run faster and through wrapping an ONNX is huge. So it's a no-brainer for us to deploy things like that through ONNX, but with something that's deployed in scikit-learn and has a lot of like internally baked tokenizers and like references to internal computations of data that's represented in weird ways. It's a little bit more of a migration hurdle to execute something like that.
got it. So just to rephrase it, since like some models are very easier to convert, that then Tensor the value is super high. But if it's like too super complicated to convert, then you guys just stick to the data. Like
yeah, I think the equation there is just around the amount of time that we've budgeted for doing this kind of a migration like this has to compete with all other kinds of engineering considerations. I think ideally we would like to standardize. I don't think that the extra complexities are such that they're worth the like performance improvements that they would drive over using something more standard is worth the additional complexity of maintaining multiple serving formats. It's just about the amount of engineering time that would need to be put into figuring out how to execute the migration.
got it. No, this is super helpful. And the next question, a little bit more on like the inference workloads, right? So do you have like your own, since you have built your own infra, like do you have support for different scenarios like real-time batch and streaming, or is it like a single API which you use for like all these three kinds of serving, or have you built like different consumers for like all of these?
Yeah, I mean, we have all three. Our streaming and real time are largely the same pipeline, in that it's just different sources by which the actual calls get made, whether it's through Kafka or through like a direct API call. Whereas batch is quite different because it's deployed through Spark. The the biggest challenge is parity, not just of the model's inference, although that is a challenge, but also of the features that get joined. In general, the feature parity tends to be a substantially larger consideration than model inference parity, from the aligning what's going on in batch and what's going on real time, because we have so many things that deal with aggregate features. That's like a lot of our core detection strategy is to understand how strange a particular message is in the context of a particular organization's environment. This helps us be able to detect whether or not certain actions are indicative of an account being taken over or a message being malicious, based on how different it is from the normal business traffic. But understanding what normal business traffic is, especially on this day at this time, given the context of the business, requires building these aggregation systems that consume lots of events what's going on in this business, and present a sort of unified aggregated picture of what is the current state of the types of things that normally happen and types of things that are happening recently, and how does this compare to what's happening in this particular event. And so that's this point in time reference on what was happening at exactly this point in time when this inference was made. And so the way that those features get joined in a batch setting, if we're trying to predict multiple things that happened at multiple different points in time, that's a very complex join. And there's some amount of noise that's, you need to do some kind of bucketing. There's just sort of a fundamental difference between what's going on in batch versus this time travel join has this quantization of time that's not representative of what's actually happening in real time versus what's happening in real time. So this is the fundamental difference between the two settings. I think it tends to drown out, the size of that difference tends to drown out the other types of differences that we see within these.
Got it. So since your batch inference is a little bit more tricky, you are saying, than a real time and streaming, because again, if you're trying to batch multiple events together, the feature store, the time series data of that is not represented in the best possible manner, although you guys must have been doing something to do that. Is that a correct understanding?
Yeah, and I think that this is a pretty fundamental challenge with batch versus real time, because we face the exact same issue at Twitter. At Twitter, there's one of the most important features when deciding how to rank an ad or how to rank a tweet was, what has this person been doing recently, and what has happened, what's the most recent actions that they've taken. And so that requires this kind of time travel identification of given the time of this event happening and what this user has been doing recently, the alignment of that event that's representing that feature. And so reconstructing that in a batch setting versus a streaming setting is quite complex and often tends to introduce discrepancies.
Got it. And so no, this is pretty interesting, and I think a very unique organization that has this kind of scenario. Yeah. So just my next question on a little bit on model serving runtime, right? So are you using something like a Towards script, TF serving, or something like a container, or have you written the custom scripts to build your containers from scratch for the serving framework?
Yeah, right now we're building from scratch. We've considered utilizing Triton and TF serving at different points in time. There's a lot of eccentricities with our environment. The biggest thing is that we don't have a clean separation. For most of our models, we don't have a clean separation between how we do feature preprocessing and how we do model inference. We don't have a standardized representation of the features that are attached to a particular event that we would hook up between the one serving runtime, one service hosting the serving runtime, and the different one that's doing the featureization, feature extraction. That's largely a deliberate decision. The identification and extraction of such an API introduces complexity in how you add new features. It makes it a little bit more complex to there's more services that need to be deployed when you make changes to features, when you add features, when you change the schema. And the more schemas that you add, the more friction you add to making these changes. There's huge downsides, obviously, because it adds a tremendous amount of complexity into our deployment environment, because we need to maintain both the models that are running and the feature preprocessing code. But the benefit of flexibility at the moment, I think, is still the right trade-off. This was very different to Twitter. At Twitter, it was the TF serving was the solution that we utilized. It was entirely separated. And as a result, adding new features was a very long and arduous process. But the model inference was much cheaper. And so the model inference at Google is much more expensive because we maintain this flexibility. So there's a big trade-off in this kind of like flexibility versus efficiency. And we've opted for flexibility at the moment. I don't think we're too far from the state where we would switch to the sort of more stable approach, but it has a slew of costs on go forward productivity and flexibility, and so that's the main reason that we've treaded lightly around making that shift.
Got it. No, this is pretty interesting since again you have done both ways, so it's great to understand that what is the right switch between flexibility and efficiency. On this, just one more question. Often people also like struggle, like another fight is between latency and model accuracy, right? So you can make a very big model which runs very like it takes a lot of time and compute, and then there's like a low latency model which you can train on a smaller data set, but again the accuracy wouldn't be so good, right? So just wanted to understand that how do you guys make decisions in your current org, and I just wanted to understand things around that.
Yeah, so this is a really relevant issue for us because when you think about like different kinds of cyber attacks, this is a different kind of challenge. But for email in particular, there's this notion of an email gets delivered, and we need to make a decision on that email pretty quickly. And if we wait too long, either the person will have to wait for their email to, if we're overly aggressive and we pull it before running all of our models, and we need to wait before everything's run and before redelivering it, then the person has a longer period. We introduce business disruption by doing this to safe emails. And if we wait too long to remediate a bad email, then we produce a bad customer experience as we leave the customer at risk while a malicious email sits in their inbox. They might have malware or something attached to it before we make a decision on it. So both of these are really important. There's actually a third dimension on cost that's also important to manage, which is sort of just that there's a certain cost per mailbox that we need to maintain, and there's increases in costs can decrease latency. Latency and cost often will go up together when you have, if you're just like dealing with model size, they'll increase together. But there's a lot of consideration. There's a lot of things that will affect one and not affect the other as you make like different changes to how models are deployed. So we have what we normally do is like a multi-stage scoring system where we utilize multi-stage scoring both for latency benefits and for cost benefits, where we'll drop certain events from our pipeline based on the predictions of lighter, faster models earlier on. So that's one tool that we utilize to balance these. And like in cases where we don't think that accuracy is going to be impacted based on really high confidence lighter predictions, we'll drop it earlier. For us, latency, just given the dynamics of latency, where it's something that's very attached to the customer experience, it's something that matters a lot at a certain point, but doesn't matter a lot at a lower point. Like if we're dealing with the difference between like 200 milliseconds versus 400 milliseconds latency, it doesn't matter that much. Even like a doubling of latency from 200 to 400 milliseconds does not really affect the customer experience much. This can be a big impact on costs, depending on where that latency is coming from. If it's just like additional CPU resources, but in terms of like the impact of the customer, it's not huge. Going from 5 seconds to 10 seconds is a huge impact on the likelihood that like a bad email will end up getting clicked on and read, or 2 seconds to 5 seconds. So they're really very different on different points of the curve and where we'll make this trade-off. So this is something that we don't have like a single rule of thumb. We kind of have to evaluate each case individually. Different kinds of attacks, like there's some types of attacks that are very simple and very high volume, where attackers will attack like hundreds of thousands of accounts at once. There's other kinds of attacks where will be a extremely highly engineered attack geared at executing like a $10 million fraud. And these have very different trade-offs in terms of accuracy and latency, where we're much more likely to sacrifice cost? Is it sacrifice cost, sacrifice latency to get maximal accuracy on a really high targeted attack than on something that's a more commodity attack?
No, this is super
Got it.
interesting.
Yeah. No, very interesting approaches, I must say. So I have a question regarding auto-scaling, Dan. So how do you manage and scale your infrastructure for inference as your usage grows?
So we pretty carefully monitor the utilization across our different cloud environments. We have we manage everything with Kubernetes, and we have a pretty predictable usage pattern at different points in during the day, given just the sort of geolocation of our customers and the nature of business communications having like a pretty clear seasonal pattern. And so we're able to do a reasonably good capacity prediction. We make use of spot instances and similar strategies for handling upscaling when necessary, and we utilize a semi-real-time architecture to avoid overloading and give the system the ability to auto scale to pick up things that are left off in the queue. I don't think there's not a tremendous amount of aggressive innovation in the scaling. I think a lot of this is because of the relatively predictable nature of our traffic. It's a little bit more around making sure that we're making use of best practices.
Got it. No, makes sense. And finally, my last question is that can you discuss any best practices or tips for other ML engineers who are looking to deploy their models in production based on your experience?
Totally. So I think that one thing that's very critical is to deploy often and early in the ML engineering lifecycle. I think that this is a piece of advice that I feel like I've been giving throughout my career, and people have been receiving it better and better over time, because I think earlier in the life cycle of ML as a part of business processes, ML engineers were tended to be a little bit more separate from the software life cycles. And I think that now most organizations generally accept that it's a little bit better to have a closer interface between data scientists and ML engineers training models and people who are deploying them into production. I think this varies in different industries, different kinds of companies and such. But the benefits of early deployment and fast deployments is that you can better understand what are the actual deployment challenges that you will face. It can be very difficult to predict these, because sometimes your issue is offline-online mismatch, where what you're seeing offline, what you're seeing online are going to be different, and that's going to be different because features getting served differently. It's going to be different because the online and offline environments are different, and there's an enormous slew of differences. Sometimes the issue will be that your actual deployment is harder than you thought. Maybe you thought you'd be able to do an automated deployment and you can't, and that makes it difficult for you to automatically retrain your model, for instance. That can be a major challenge to deal with, and it could be a very serious software challenge on just a deployment environment alignment. Sometimes you are going to run into challenges where your model deployment is much more expensive than you expected, and you need to optimize, and it's either slower or more expensive, and perhaps it didn't show up offline because of one aspect or another of how you'd estimated these kinds of costs or latencies, but it does show up online, and the slew of different online challenges that you can face is massive. And so I think taking a experimental mindset is the biggest and best piece of advice that I would give towards the deployment process.
Makes sense. No, very interesting. I think I'm sure that a lot of people who are listening to this episode will benefit from this. So yeah, I think this is it from our side, Dan. Again, thank you so much for taking out time for this session. I think I also got to learn a lot of interesting things and techniques here. So yeah, thank you so much.
Absolutely. Happy to have had the opportunity to speak with you. Thanks.
Great.